Okay, here is today's lesson. And today's lesson is about learning what factors affect acceleration. So, you already know this. Unbalanced forces cause acceleration, right? But now we need to understand, what factors determine the acceleration, right? So, for example, I'm going to go to this picture right here, okay? I'm going to push on this object and it should accelerate, okay? So if you draw an FBD of this object, you will have normal from the ground. Gravity, of course, is always gravity. Then there is the force from my finger pushing it that way. And if there's no friction, let's just say there's no friction, so there's no backwards arrow. So this object clearly has an unbalanced FBD and thus will accelerate. Now, what factors will determine the acceleration of this object? Okay. Now, one factor is super obvious. So if I'm pushing this with my finger and I'm pushing with a certain force, what if I want to increase the acceleration of the object? Well, one obvious thing would be to push harder. So if I make this force arrow bigger, clearly that guy should accelerate faster. Hopefully that makes sense. That intuition is totally correct. So yes, if you provide more force, this thing should accelerate greater, okay? For sure. So yes, one thing we can say is that the force affects the acceleration, all right? And such that more force means more acceleration, all right? Fair enough? Okay, now another thing I could do to affect the acceleration of this object without changing the amount of force is something that we talked about on Friday. And remember, there is a property of this cart that determines how difficult it is to accelerate, okay, right? And that is the mass of this cart. So if I were to somehow able to change the mass of this cart, I could change the acceleration of the object. And how could I change the mass of that cart? Okay, well, I could just load it up with mass. So put little masses on top of it. Or load this, put little things on top of it. Let's hold on. Okay, grab that guy. There you go. I put these guys on top of it. Okay, I don't know how that balanced there, but still. Okay, so now this has more mass, and now when I push it, okay, well, the fact that we learned on Friday that if you have more mass, it is hard to accelerate, right? So even if I push with the same amount of force, that acceleration of the object will not be the same anymore. Why? Because it has more mass, right? And as you learned on Friday, the other thing then is the mass affects acceleration. Like I said, as you learned on Friday, if you have more mass, this should result in less acceleration. Acceleration, all right? So let me go back to the screen then. What factors affect acceleration then, all right? And the two factors that determine the acceleration are the force you apply onto the object and the mass of that object. Okay? And like we just said, more force means larger acceleration, more mass means smaller acceleration. Now you can encode these two relationships into one equation. So say you want to make an equation that tells you what acceleration depends on. Well, it's going to depend on both force and mass, right? So you should have both force and mass somewhere on this side of the equation, all right? And what you see right here is what's sometimes called a direct relationship, that if you increase the force, you increase the acceleration increases. So they have a direct relationship. And this is something called an inverse relationship, where if you increase that, this resulting factor actually gets smaller, okay? So you can put these two into one equation that determines the acceleration, all right? And so our job is to then figure out where F and M belong in this equation. And just a little bit of a tip, one of those factors is in the numerator, and one of them is in the denominator, right? And then hopefully you can kind of see, it should be kind of obvious. Actually, let me change that color to blue. All right, so that the variable that is in the numerator should be the one with the direct relationship. And the variable that's in the denominator should mean the inverse relationship, because that's how fractions work. So clearly it seems to stand to reason that F belongs in the numerator and M belongs in the denominator, right? Because if you remember how fractions work, if the numerator gets bigger, this number gets bigger, right? But if the denominator gets bigger, this number gets smaller. So this seems to be a relationship that reflects these two things, all right? So hopefully this relationship here makes sense. A equals F over M, all right? This relationship is called Newton's second law, okay? So we already talked about Newton's first law. Newton's first law was just saying that forces cause acceleration, right? Newton's second law is actually an equation that codifies exactly how you calculate the acceleration and introduces this idea of mass into the relationship, okay? This sigma variable is something I'll talk about later. You don't really need to know that for today. So let's just look at this. Acceleration is equal to force divided by mass. And you see this A represents the acceleration of the object, this F represents the force on the object, and this M represents the mass of the object, okay? So let's see an example of how we can use this, all right? So let's just say you had an object right here. It had a mass of 5 kilograms. Right? You apply a 40 Newton force onto this object, because remember, units of mass is kilograms, units of force is newtons. So if we want to find the acceleration then, we just have to do A equals F over M. So you do A equals F over M, F is 40, M is 5, and you get 8. And if your units is newtons, of force is newtons, and your units of mass is kilograms, you will get meters per second, all right? So this will get 8 meters per second. Pretty easy to use, right, at this stage? Okay. There are some little twists that I want to kind of point out. Once again, here's the Newton's second law. And then there's kind of questions that involve what are called reading the equation. So I want you to sort of look at this equation and not just think of it as, oh, something I can plug numbers in to find the missing variable, right? Although there's going to be a lot of that, right? If I give you any 2 of these variables, you should be able to find the third one, okay? Just simple algebra, all right? But this equation is more important than that. It describes relationships between variables, okay? And they're going to be kind of questions that ask you to sort of read this equation. Like, what do I mean by that? So how about this? If you double the force, what should happen to the acceleration? And the way you answer this is you have to sort of ask yourself, are those 2 variables linear with each other, okay? And the way you answer that question is, well, do you see any weird exponents or something like that, all right? And so there's no exponents in that. So this means that they are linear. A and F are linear. Now, what does being linear mean? Well, that means if whatever you do to one variable means that's the result that happens on the other variable. So in this case, if you double the force acting on the object, the resulting acceleration of the object will be doubled. Okay? And likewise, actually, this question is if you double the mass. Now, mass is an inverse relationship. So if you double the mass, the acceleration should go down. So you wouldn't say double the acceleration too, because the acceleration clearly goes down. So the question is, well, by what factor does the acceleration go down? All right. And one way to do this is knowing that it's an inverse relationship, you have to just take that factor 2 and you invert it. In other words, you take the reciprocal, which means the number when you invert 2 is 1/2. And so that means what happens to the acceleration, you get half the acceleration. And of course, multiplying something by half does mean it gets smaller, okay? So, if you double the force, you double acceleration. If you double the mass, you get half the acceleration, all right? That's what I'm trying to tell you with these symbols, okay? All right, so kind of things that you can answer like this. What if you triple the force? If you triple the force, well, it's straight up linear, so you triple the acceleration. If you triple the mass, you have to invert it, and you get 1/3 the acceleration. If you quadruple the force, you quadruple the acceleration. If you quadruple the mass, you get 1/4 the acceleration. So it's 1/4 the acceleration, right? Okay, so there are questions like that that you need to be able to answer, okay? So like, for example, here's another question, all right? Say you apply 40 newtons onto an object and it accelerates at 5 meters per second, all right? What would happen if you apply 80 newtons? Well, there's a couple ways to answer this question. One way that's actually more a long way, and one way that's quick and easy, all right? Here would be the long way to do it, all right? So, A equals F over M, correct? Well, you have F and you have A, correct? So you can plug those in. And that allows you to solve for the mass, right? So to solve for the mass here, you multiply by m to get out of the denominator, then you divide by 5, right? So you multiply by m, you'll get 5m equals 40. And then you divide by 5 to get m alone, and you'll get 8 kilograms, right? And then you could do all those same steps again, but this time with that same mass, use a new force, right? Same mass, new force, and you get the new acceleration, all right? Now, the advantage of actually understanding how to read the equation, the quicker way to do it would be to see, oh, well, the force doubled. So if the force doubles, what happens to the acceleration? Well, the acceleration doubles. So that's why you get 10 right away. So being able to read the equation allows you to kind of skip a lot of work sometimes, all right? So it's kind of important to be able to just sort of think about how you can sort of read the equation and kind of understand, right, relationships between variables rather than just plug numbers into equations, all right? So that's done with my lecture. So now it's time for you to just work on the practice worksheet. All right, thanks.